Alrighty, everyone. So today we are going to be looking at finishing up our Unit 3 exponential functions unit with a set of notes focused on how we now use exponential functions. Since we have learned about growth and decay, we've learned how to interpret the different parts of a function. We've learned how to create exponential functions from a word problem. So now we're going to go through and actually use those functions we've created. So we're going to name this using exponential functions. For me, in my notebook, this is going to be on page 20. In your notebook, make sure you are taking a look at what page your 3.4 notes are going to end up on. Now, for today's set of notes, we are going to need a calculator. If you're doing this in the classroom, we should have calculators around the room for you. But if we've run out of calculators, or if you're doing this from another location and you do not have a calculator readily available to you, I'm going to show you a tool you can use online. I have found that while it's a little bit wonky on my phone, this tool also does work on my phone and is completely free. So we know in a lot of cases now, when you're taking a standardized test like the MAP assessment on NWEA, or even the SAT has moved online, you end up getting your calculator online as well. And so this tool is available as long as you have an internet connection, and you can use this tool to practice using that calculator online and get practice with your TI-84 calculator. So we're going to come to TI-84calculator.net, click launch, and there, there are a few kind of steps we need to take here because there have been some updates. So we're going to go here to testnav.com, click through to the first question. And then if you look at the very top of the screen, this center calculator button is your TI-84 Plus. There are other calculators here. There's the basic scientific calculator if you needed to get practice with that. And there's the Desmos graphing calculator if you wanted to get practice with that as well. Today we're going to use that TI-84 Plus calculator because that is going to be give us the best calculations and the easiest way to put in calculations for our exponential functions. You could use the scientific calculator as well, but it's a little bit more fussy than just doing this in the TI-84 Plus calculator. So make sure you have a calculator with you so that you can do the calculations along with me. And let's go over to our notes. So I'm going to leave that up. And heading back over here into our 3.4 notes. So this is our using exponential functions. This is, if you're in my class right now, this is the last lesson within this learning target. I can use exponential functions to model real-world phenomena. So let's take a look. We're going to remind ourselves one more time and write them down one more time of the general formats. The two general formats we can use of the exponential functions. The first one was our a times b to the x over n, where b is the base, a is the initial value, the starting value, and then the x over n is the, typically a lot of times with real world functions, we use time over some interval of time, but that's our exponent. How often is b getting multiplied? And then the other format we can have is a times, it just adjusts the base a little bit. So instead of using b, we can use 1 plus our growth or decay rate r, also to the x over n power. And when we see this one, we're going to use this one more when we are working with a percent increase or decrease, or if we're looking for at what percent did this situation increase or decrease. which we did write down in the last set of notes, but let's just remind ourselves here. You're going to use this, this specific format more when you're working with a percent growth or decay. So the steps for this are actually really quite easy, especially if you've already done the creating exponential functions video. The first thing you're going to do is create your equation after you've read through the problem. And then we're going to use the equation by substituting what we know. Forgot how to spell for a second there. Substituting, there we go. Substituting what we know and then solving for what we don't know. So let's take a look here. Example number 1, the half-life of a radioactive kind of nitrogen is 10 minutes. If you start with 120 grams of it, how much will be left after 20 minutes? So just to note, when we see half-life, automatically we're going to know that the base is 1/2. A half-life is how long it takes for something to be cut in half. Typically an amount of something being cut in half. And the half-life itself here, it says is 10 minutes. That's the n. That's the interval of time. So here our n is 10. I see I'm starting with 120 grams, so that's my A, 120. And how much will be left after 20 minutes? That's going to be, in this case, my x. My x is going to be 20. So if we were to create our equation or our function first, we could start, let's see, it's nitrogen. We could start with n of x equals our starting value of 120 times our base of 1/2 to the x over 10 power. But then we know that we're looking specifically for 20 minutes. So we're going to, how much is left, how much nitrogen is left after 20 minutes. So we're going to substitute 20 in place of that x and get 120 times 1/2 to the 20 divided by 10. And we can put this whole expression right into our calculator. So we're going to take this 120 times 1/2 to the 20 divided by 10. And let's go over to our calculator. So we'll type that in, 120 times 1/2. So that's just 1 divided by 2. Our exponent is this little up caret on the top, on the right side below your clear button, right above the division. And we can put that 20 divided by 10 right into the calculator. Pressing enter, we would get that we have 30 grams of nitrogen left after those 20 minutes. Going back to my notes, going back to my pen, there would be 30 grams left. And we want to make sure we're using units here because this is some type of contextual situation. So it's not just 30. We have 30 grams of nitrogen left after those 20 minutes. Let's look at another example here. So condos in Georgetown, let's just say, I don't know that this is true, but let's just say condos in Georgetown go up in value by 10% each year. If your family's condo is now worth $1,200,000, what will it be worth in 8 years? As we're thinking about this, it doesn't say it in the problem, but just to think about values of homes, let's round this to the nearest 1,000. We're going to round this to the nearest 1,000. Just because typically you don't go down to like the dollars when you're thinking about the worth or the value of a house. So let's break down what we have here. So we're going up in value by 10% each year. That's going to be our R. Our R is 10%, which if we divide by 100 would give us 0.1 because we want to be in decimal format. Our starting value is 1,200,000. That's going to be our A. Each year, that's our N, right? That means N is 1. And we're looking for what will our house be worth or our condo be worth in 8 years. That's going to mean X equals 8. So let's start by writing out the general equation for the value of our condo. So let's have C of X for condo equals that starting value of $1,200,000 times, and since we had our increasing rate here, we're going to take that 1 plus 0.1, getting that from this format here. 1 plus 0.1 to the X power, and we don't have to put that over 1 because we know if we divide by 1, that's just it's not going to change anything. And then, so this is the general format of this equation, but we're specifically looking for what our condo will be worth in 8 years. So we're looking for C of 8. That's going to be 1,200,000 times 1 plus 0.1 to the 8th power. And remember, we're going to round to the nearest thousand here. So if we go back to our calculator, we can put that in 1,200,000. And we can even type in here the 1 plus 0.1. We don't even have to do that separately, or we don't have to do that addition. We can make the calculator do the addition for us to the 8th power as our exponent. And that's going to give us $2,572,306.57. However, we did ask for this to be rounded to the nearest thousand. So I see 2,572,000. And after that 2 is a 3. So I know my rounding, I'm just going to keep it at 2,000. So to the nearest $1,000, we have $2,572,000. So after 8 years, if your condo increases by 10% every year, this family's condo will be worth more than $2.5 million. Wouldn't that be nice? Let's look at one more example, and this example is going to have a little bit more work involved, but I still want us to go through. We will have enough information to be able to still solve this problem. When Richard moved to Clover Hills 1 year ago, it had a population of 3,650. Today, the population has increased to 3,869. And it is expected that the population will continue to increase each year. Write an exponential equation in the form y equals a times b to the x that can model the Clover Hills population y x years after Richard moved there. So when I look at this, I'm noticing right away that I'm not given a base. I don't know what the increase or how much it's increasing by every single year. However, I am noticing I'm given the initial value and I'm giving the value 1 year later. And that allows me to find my base. It's specifically telling me to write the exponential equation, so I know to expect that this is an exponential equation. So what we can do to find the base, b, is to take the new value and divide it by the starting value. So in this case, that's going to be 3,869 divided by 3,650. And that's going to give us the whole base here. So let's go to our calculator and do 3,869 divided by 3,650. And I get a base of 1.06. So my base here is 1.06. Now let's talk about this 1.06 for a moment, just to make sure we understand what it means. When we're using the format for an exponential equation, in this case, when I see a decimal like this, I like to think about this second format, a times 1 plus r to the x over n. So my 1 plus r, my base, is this 1.06. So if we break that up, that's telling me that I have 1 plus 0.06, right? I have that 100% of whatever the population was last year plus 0.06. So this is telling me I have a 6% increase. Now, you don't necessarily have to know this to solve this problem, but we want to make sure that we can take that rate and work our way backwards to see what the actual, or continue working, I guess, to see what the actual percent increase was. So in this case, the population of Clover Hills is increasing by 6%. We still don't have our exponential equation yet. So let's go back and finish that up. So the population, this asked us to use y, equals our starting, our A was 3,650 times our base of 1.06 to the x power. And there is my equation for the population of Clover Hill. Now, the second part of this equation, to the nearest 100 people, what can Richard expect the population to be 4 years after he moved there? So now I know, using that equation, that x equals 4. So we're going to do that substitution. Y equals 3,650 times 1.06 to the 4th power. And we can go over to our calculator. 3,650 times 1.06 to the 4th power. 4,608. However, this is specifically asking us to the nearest 100 people. So I need to round this because I have ones in this answer, and it wants me to stop at the hundreds. So if I look at the hundreds here, the 6, a 0 comes after the 100. So we're going to round this to 4,600 people. So after 4 years, Richard can expect the population to be about 4,600 people. Go ahead and take a moment to put this into your notebook and then go back to Canvas to see what assignment comes next.